Okay, the objective of this little tutorial is to derive the equations of motion for case study 1. And you may remember that in this particular case we have a rod of length L and mass M that's spinning, and we've got our angle theta, and then we're applying a torque here, tau. And there's some opposing damping. So there's, damping with a damping coefficient B. So the idea is to do the equations of motion. The first thing we need to do is come up with the configuration variables. And in this case, these are the things that are coordinates, I guess. These are the variables that change with time. In this particular case, Q1 is going to be equal to theta. We also need the generalized forces. And in this case, the generalized forces are tau 1 is equal to the applied torque tau minus damping times the friction. So this is a viscous friction term. We also need to derive the kinetic energy. So this is a system that is spinning, so the kinetic energy K is going to be 1/2 omega transpose J omega. And since in this case omega is equal to 0, 0 theta dot, this term is going to be 1/2 Jz theta dot squared, where Jz is the 3×3 element of J. So to do the kinetic energy then, we need to find Jz. So Jz is computed by looking at the the inertia of this mass spinning about its endpoint. This will have length L, mass M, and we'll assume that this is small. Therefore, Jz is going to be the integral from 0 to L of x squared, y squared is going to be 0, dm, and dm is going to be the mass of this little elemental piece of width dx, so it'll be the density, which in this case is mass over L times dx. Therefore, the inertia then is integral 0 to L of x squared m over L dx, which is m over L x cubed evaluated over 3, evaluated from 0 to L. And so we have mass L squared over 3. Therefore, the total kinetic energy is 1/2 mass L squared over 3 times theta dot squared. Next thing we need to do is compute the potential energy, and the potential energy is equal to, potential energy is some initial or nominal potential energy plus mass times gravity times the height of the center of mass. This will be, in this case, the center of mass. And if we go back and look at our little figure here, the height of the center of mass is going to be L over 2. So the center of mass is at the center here times the sine of theta. So the total potential energy then is equal to P0 plus mg L over 2 sine of theta. Okay, so now the next step is in deriving the equations of motion, is to find the Lagrangian. So the Lagrangian L is the kinetic energy minus the potential energy. So in our case, it's 1/2 mL squared over 3 theta dot squared minus P0 minus mg L over 2 sine of theta. Okay, so that's the Lagrangian. And then the next step is to compute the Euler Lagrange equations. So Euler Lagrange. The Euler Lagrange equations are d dt partial of L with respect to Q, in this case just Q1 dot, minus the partial of L with respect to Q1 equals the generalized forces. And so, and this is where we consider Q1 dot and Q to be separate variables. And in our case, Q1 is equal to theta, so this equation becomes d dt partial of L with respect to theta dot minus the partial of L with respect to theta is equal to tau 1. So let's come over here and just compute some of these quantities. So the partial of L with respect to theta dot. Now here we consider, we only look for places where there's a theta dot. So we think of theta dot and theta as being separate variables. So when we take the partial with respect to theta dot, we're only worried about this term. And so we get ml squared over 3 theta dot. Now theta dot is actually a function of time. So when we take the time derivative of the partial of L with respect to theta dot, that gives us ml squared over 3 theta double dot. Where theta double dot, is the second derivative of theta. Okay, partial of L with respect to theta. Now we again go back to this formula and only look at this last term, which is a function of theta. So the partial of L with respect to theta is going to be minus mg L over 2 cosine of theta. Okay, so now we're ready to plug into the Euler Lagrange equations here, and in that case we get ml squared over 3 theta double dot plus, because of the minus sign there, mg L over 2 cosine theta is equal to the generalized forces, which in our case is tau minus b theta dot. And the generalized form that we're going to look for here will be to get all of the theta dots on the left-hand side of the equation. So we're going to write this as ml squared over 3 theta double dot is equal to tau minus b theta dot minus mg L over 2 cosine theta. So this formula here is the equations of motion for the for case 1, this one-link robot arm.